Earlier we talked about the frequency response of an LTI system. Given the impulse response of an LTI system, here's how the frequency response can be obtained from the impulse response. Here Hn is the impulse response of an LTI system. Now, if we use this same formula, but we plug in an arbitrary sequence Xn, not necessarily an impulse response, an arbitrary sequence Xn, then what we get on the left-hand side is what we call spectrum of the sequence. The spectrum, or DTFT, DTFT stands for discrete time Fourier transform, of a sequence Xn is defined like this when the summation converges. With the frequency response here, they are exactly the same thing. So, if this is the impulse response of an LTI system, we said this is a frequency response of the system. And if this is an arbitrary sequence, we say this is the spectrum of the sequence. From the sequence, we can compute the spectrum. This is called DTFT. And from the spectrum, we can also compute the sequence. This is called inverse DTFT. We have the spectrum here on ej omega n, d omega over 2 pi, integrated over a 2 pi period. Like the frequency response, the spectrum of a sequence is a complex number for each omega, and we can express it in polar form, magnitude and the phase. The magnitude part is called the magnitude spectrum, and the phase is called the phase spectrum. And this sequence and its spectrum is called a Fourier transform pair. Sometimes we just say Fourier transform skipping discrete time if it's clear. If it's clear from the context that we're talking about discrete time Fourier transform. The spectrum has all the property that we mentioned for frequency response, like it is periodic with a period 2 pi. From the sequence, we can always compute the DTFT xej omega. That's no problem. But how do we know that integrate the spectrum like this? What we get is the sequence itself. This requires some proof. To prove IDTFT, let's recall Fourier series Fs for continuous time function, a periodic function f of t, a continuous function with a period t, can be expressed as a summation like this, and the coefficient ck here can be determined from f of t like this. And the coefficients are called Fourier series coefficients. Let's take a good look at each term in the summation here. Let me write it down again. Each term is of the form. What is this? This is a exponential function, isn't it? That's an exponential function. So each term is an exponential function scaled by this ck here. And what kind of exponential function is this? It's an exponential function with frequency, k times 2 pi over t. So each term is an exponential function, and the frequency of the exponential function is a multiple of 2 pi over t. So a periodic function with a period t can be written as a linear combination of exponential functions. And each exponential function has frequency that is equal to a scale, a multiple of 2 pi over t. So how can we use the result? We do have a periodic function here. The spectrum is a periodic function with a period t equal to 2 pi, and it's a function of omega, a continuous variable. So now we can use the Fourier series result. Using Fourier series result is said it can be written as a linear combination of exponential function, and this exponential function is of the form 2 pi over t. But now t is equal to 2 pi, so they cancel off, and we get omega. Now if we compare these two summations, we can see that they are very similar with a slight difference. Here the omega function here is minus j omega n, and here is jk omega. So let's make them even more alike. We can write it as using n equal to minus k, then this is n minus c minus n, and ej minus n omega n. And we can compare this one and this one, and we see the exponential function part is the same. So the coefficient xn is equal to c minus n. What is c minus n? Using this formula here, we can just plug in the spectrum and see what we get. C minus n would be 1 over t, t is 2 pi. F of t now is x e j omega, and we have j, 2 pi over t, so they cancel off. We get n omega, d omega, and then we integrate it over a 2 pi period, and that's the inverse Fourier transform formula that we have earlier.